So cloud computing is a kind of technology that's come along. And there are lots of different ways you can describe cloud computing. If you go to NIST, they have a lovely description about cloud computing. I like to think about it in much simpler terms. I like to think about it in terms of having instant access to an infinite or near infinite amount of computing and data processing capability. Okay. So when people talk to you about cloud computing, this is how you should think about it. Instant, infinite, okay, on demand, accessed over a network. Okay. Everything else comes under that. But this is the fundamental sort of principle of cloud. And what that means really is that for your careers as young researchers and as postdocs and fellows moving forward, cloud computing is the default computing platform for all of your research. Okay? This is without doubt. In the next 10, 20, 30 years, cloud is it. Okay? And you're in a very good position to be able to jump on this and get ahead. When I started my career in high-performance computing and doing computational fluid dynamics, we started building PC clusters. We were using 486 Pentium machines, using 10 megabit Ethernets with hubs, not even switches, to do high-performance computing, and people laughed at us. The big supercomputer manufacturers laughed at us and said, this is crazy, this isn't going to perform, there's no way people are going to use this. Today, just a couple of weeks ago at the supercomputing conference, the top 500 computers, over 95% of the supercomputers on the planet use that technology and that paradigm. Okay, we're at a similar point, or probably beyond that point, with cloud computing today. This is a picture of New York taken in 1905, okay, at the junction of Fifth Avenue. Take a look at this picture. You can see horses and carts and trams. Okay. This is the same picture taken 20 years later where you won't see a single horse and cart. We're undergoing a similar revolution right now with computing, particularly for applications such as data science. And that's why it's super exciting that we're working with you at the Turing. And we have this program called the Cloud for Global Good, if you look online, which is Microsoft's view of the world, which is we're kind of on a journey with cloud, and there are a lot of issues, not just on the technology side, which is very exciting, but also on the policy side, looking at things like ethics and security. And so we've just started this program called Cloud for Global Good, working with researchers, working with companies, working with governments, to look at how this cloud computing revolution can go forwards in a sensible way. From a research perspective, we kind of have a view at Microsoft Research, and we coined this phrase, let researchers be researchers. The majority of researchers really have access to computing power on their desktops, on their laptops. Some people are lucky enough to have access to large supercomputing facilities, things like Archer and Prace. People have access to university clusters, and here at the Turing, fortunate enough that obviously all of the founding partners have their own great facilities. But by far the majority of researchers don't have access to that. Not just physical access, but often having the skills to be able to make the most of that. This is really still a real niche skill set on using supercomputers. And when you're generating lots of data, you want to share that. You don't just want to share the data, you want to share the methods and the algorithms and the code. And if you can't do that, reproducibility of research is really hard, or actually pretty much impossible. And where we are today with reproducible research and open science is really at the start of that journey. And so what we think is that there is this shift where cloud computing can really help. Well, we don't say get rid of exascale supercomputers. We still need those to do those very large numerical problems. But we can take the data from those machines, make them available to the wider community to do data science on it, for instance. Do machine learning on weather and climate forecasts, not just look at the Newtonian mechanics, but can we apply some AI to better understand things like climate? Okay, so we're moving into this world where we can share data, share results, where reproducibility becomes the default. Okay, and we can share. And so that's why we're really excited that Microsoft is partnering with the Alan Turing Institute. This is Andrew Blake. He was actually sharing the stage with our CEO, Satya Nadella, a month ago, where he announced that you would get access to the Microsoft Azure cloud for your research, which is why I'm here and why I'm spending time here at the Turing. And this was the official announcement from the Turing, but other places like Tech Republic and the newspapers also reported and very excited by the fact that we were working together so that we can accelerate your research. And also for us, understand how researchers can make use of the cloud so you can actually influence our own thinking around cloud computing as well. And one of the things with cloud computing is the sheer scale of it. I have to update this slide. I had to update this slide last week because the number of regions jumped from 34 to 38 a couple of weeks ago. This is our hyperscale cloud. There are only really kind of 3 companies in the world that have a cloud as big as this and as widespread as this. The lines connecting them are our own network, okay? Not the internet, but our own private network that spans across these data centers. And these data centers operate Microsoft Azure, but they also operate things like Office 365. When we deliver something like Windows Update to 1 billion users, it's flowing out through these data centers and a lot of edge data centers as well. So when we think about this, and you think about this in a research context, it means when you're collaborating with other people, you can deploy things here in the UK, but you can redeploy them in Brazil, Australia, and then other researchers around the world can use what you've done and deploy it locally for themselves. So this idea of hyperscale is really transformational in how we think about research, particularly in an international context. But with that, you also have to have trust in the cloud. And it's one of the things we really pride ourselves on at Microsoft is a real deep understanding of what people need in terms of security, in being the strongest advocates of privacy in the industry, about compliance and about transparency. And so when we work and we've deployed, we spent $3 billion on European cloud infrastructure. And part of that is deploying multiple data centers in the UK and working very hard with the government to make sure that we have compliance, we make sure we satisfy all the security and privacy, and we're also transparent about what we do. So when we think about things, particularly things like healthcare, or at the Turing when partners such as GCHQ or banks like HSBC, this is really critical. And actually, many people, and including many university IT directors, will agree that because we invest at hyperscale, that we can do this better than many IT teams can locally, because this is a significant effort. And so when we deployed our UK data centers, specifically Liam Maxwell here, pushed very hard for this, of having UK data centers. A couple of our first tenants in our data centers are the Ministry of Defence and the National Health Service. That gives you an idea of the level of trust that the government places in our cloud. And again, for research, particularly research around sort of more sensitive data, it's actually a really nice platform for that. And when we talk about cloud and we think about computing, we often think about data center infrastructure. And I think about this back to my days as a PhD student when we were literally putting boxes on shelves. And you have a lot of infrastructure there. And when we think about cloud, we often think about this idea of virtualization. So thinking about the idea of abstracting the hardware layer up into some virtualization layer where you have compute, so the concept of virtual machines, and more recently the context of containers, where we can wrap an application and have it independent of the hardware it's running on. Storage, the concept of object storage rather than pure file systems that allow us to have very scalable access to petabytes and exabyte scales of data. And then the ability to manage networks in very much a software-defined way, but also routing connections through, we have something called ExpressRoute, where we can directly connect, for instance, from the Janet network into universities and again into NHS. And so when people talk about cloud computing, they often think about this. Okay, and it's really good, it's really powerful, but the paradigm is pretty similar to what you have today. You say, all right, I've got a bunch of servers or containers, I have applications, and then I can run against that. But the real value with the cloud is that we work hard to build lots of other services on top, so you don't have to worry about this. Fundamentally, if you're worrying about this, you're still a system administrator. Okay, and like I said, you're researchers, not system administrators. Okay. And so if you can spend less time worrying about system administration and more time worrying about the machine learning, or if I want to deploy a mobile app for some mental health patients, for instance, or if I want to deploy some media distribution, for instance. So the idea with the cloud really is taking advantage of what we call these platform services. So you can spend time on your research and the problem you're trying to attack rather than worrying about the security of a virtual machine, for instance. Because that's what IT system administrators do. And so this is really where it gets exciting from a research perspective. But there's a lot there. And so we've been working at Microsoft on this program called Azure for Research, where we have about 1,000 projects running worldwide using the cloud. And it's been running for a few years now. We've been thinking about what are people doing with the cloud? Where is it really helping them? And I've kind of boiled it down to 5 kind of buckets. Okay, so I want to talk about each one of these. And as I talk through these, think about from your research perspective where these slot in. There's obviously some overlap. If you're doing data science, you might be using high-performance computing. If you're doing IoT, you should definitely be using things like machine learning. So there is some overlap, but these are sort of patterns to think about. It just helps to break down that massive diagram of essentially all the toys in the toy shop into what you can actually do. The simplest one is this idea of going beyond a desktop. So if you have your own machine, and you're trying to use that to do your research, you're very constrained with the processing, the disk space, the memory, etc. So a very easy thing is to take this approach of having your own personal server or your personal workstation. And we can encapsulate those things as virtual machines. This is one thing that we've built. It's called the Microsoft Linux Data Science Virtual Machine. So it's a pre-packaged machine, okay, where we've taken some of the tools that people commonly use. So things like R, Anaconda Python, Jupyter Notebooks, Julia, Postgres databases, and loaded them all into a virtual machine, pre-packaged and preloaded all that as up to date, including things like our deep learning toolkit, Vopal Rabbit, which is developed by some of our researchers in our New York lab, New England lab. Pre-packaged it, so you can click that and deploy this machine, okay, and you don't have to kind of worry about installing all the software and things like that. But the real advantage is you then have a menu of options of what hardware essentially you want to deploy this on. And so we have this whole menu, and it's literally a menu where you can take, say, that VM and you can deploy it onto a big machine. So it might be a small machine, okay, just to play around with. But we've got machines which are optimized for CPU. So these have only got 2 gigs of RAM, but fast CPUs. We've got some machines that have got a lot of RAM, and this is very useful if you have to load everything from RAM. Not necessarily if you're doing the processing, but sometimes for doing data pre-processing or post-processing, okay? And then the H series, I'll talk about these. These are our high-performance computing nodes. So these are optimized for supercomputing. And then our N series are GPU nodes, which I will talk more about, which are very powerful GPU-powered machines. And so this is the infrastructure level that you can deploy on to do this kind of beyond the desktop model. And some researchers down in South Africa at Stellenbosch University, they have their own kind of nice departmental level cluster. It's a modest size HPC system that happens to be running Windows. And they initially were trying to deploy a MATLAB cluster into the cloud, okay, which is great because it can expand what they can do on premise. But they actually had a problem where a couple of researchers just needed a big machine to run the MATLAB signal processing toolbox. And so they literally fired up a VM for 2 weeks with 16 cores, I think, 100 gigs of RAM, and they could just hammer away at this problem just using MATLAB signal processing, just like on their desktop, and they could get these results out to the papers and their industrial collaborators. So again, a very simple, very quick win for the cloud, but actually really kind of just got them going. And so that's why I sort of like to introduce people to that idea, which is this idea of having just more compute than you could otherwise have. And then we can go to the other extreme, and the other extreme is a supercomputer. And a lot of people talk about supercomputing and HPC in the cloud, but it's really, really hard to do. But we've done it because Microsoft has an HPC team. We developed high-performance computing stack on Windows for a lot of different customers, like manufacturing customers, banks, for instance, running tens of thousands of cores, but they wanted to run Windows, not Linux, because then they just have Windows infrastructure. So this is an example of Schlumberger, the oil and gas company, where they were looking to deploy their reservoir simulation package as a service to customers. And they wanted to be able to deploy it so a customer could come in, say, right, I need to run a simulation on 500 cores, but I need it tomorrow. So they don't want to sit in a queue. And so they actually deployed it on Azure. And you can see here on the slide here that it's actually running a little bit faster than their local machine. Obviously, there might be differences in the actual hardware and generations of hardware. What's interesting is that we're running InfiniBand. So for those of you who don't know, InfiniBand is a very, very high-performance network that's used on the majority of sort of clusters, particularly university level. Very low latency, so we see less than 3 microsecond latency, and you need that to scale above 100, 200 cores for fine-grained applications. This is an example of an industrial CFD code called STAR-CCM+, running our 100 million cell model on 1,000 cores. So, and this is on demand, so you can deploy that cluster in 10 or 15 minutes and be up and running. To give you an idea, this is, we did some training at Sheffield University. This is the size of the entire University of Sheffield HPC system. Okay, so, but you can grab that on demand. And so it shows this scaling that you expect to see, but actually it's the first time that we've been able to do this in the public cloud because we've spent a lot of time getting that hardware working. And to deploy a cluster like that, we have what are called ARM templates, these Azure Resource Manager templates. And they're JSON files that basically describe what the cluster looks like, so what nodes, what networking you need, storage, etc. And this is on GitHub, and you literally click this button that says Deploy to Azure, you get a menu, you put in some details, and then it deploys the cluster for you. So we have a bunch of these ARM templates. This one happens to deploy an HPC system using a system called SLURM, which is a very common cluster management queuing system, but there are lots of other ones as well. And so it's really pretty interesting how you can do that. Now we're moving into a world of what we call containerization, so taking the idea of virtual machines, where in a virtual machine you kind of go from the operating system up, whereas containers, we really try and just wrap the application. And so one of the really common container systems is called Docker. But there are lots of orchestration systems for managing sort of lots of Docker containers. And lots of people will kind of bet on one or other of those. And at Microsoft, because we have a cloud and we want to make sure that anybody can use the cloud, we've actually partnered with several different organizations. So we have Docker, but we support something called Docker Swarm, which is a Docker orchestration system. We also support something called Mesosphere, and we also support Kubernetes, which is principally developed and designed by Google as an open source product. So we're the only cloud system that supports multiple container orchestration systems, so you can use whatever you like. And one of the things at Microsoft we do is we're very much more open than we used to be. We're actually the #1 contributor on GitHub now. Okay, and so things like we've actually open sourced the container service engine that builds these Docker-enabled clusters. Okay, so everything we're doing pretty much, or so much of the stuff we're doing now, is on GitHub, like those ARM templates, etc. So very much open, very much into Linux as a real sort of first-class citizen. Another thing we have is something called Batch, which I'll show you in a minute. And this is something called batch-shipyard, which is basically the idea of being able to deploy a bunch of containers very, very easily onto Azure, but without the idea of a cluster, really. But this is a kind of per job basis. Okay, and we have a bunch of what we call recipes here for deploying different systems. So things like Caffe, Theana, OpenFOAM, even TensorFlow, where you can just deploy a cluster immediately. And it handles things like the file system. We can use things like the Docker or GlusterFS, which is a distributed file system. So we have these recipes that allow you to deploy Dockerized systems onto things like the GPUs, okay, with common frame. You can build your own recipe here. So we'd love to see some Turing Institute recipes in here for deploying different systems. And when I talked about Azure Batch, this is what I mean. So normally what I showed you with the SLURM cluster is you would basically deploy the equivalent of what a university would be deploy, which would be a bunch of machines. You say, all right, I've got 1,000 machines. I'm going to put a cluster manager on it. I'm going to put a queue to make sure that I can manage all of the users coming in and out. The whole idea with the cloud is you don't have to worry about the resource management. You leave that to us. It appears that you have an infinite pool of resources. Okay, we have to make sure that there are always resources available. So when you do that, for deploying clusters, we developed something called Batch, which basically manage all of that cluster deployment for you. So all you do is you submit a job and you say, here's my input data and I want to run on 1,000 cores. We then spin up the 1,000 cores, run the job, ship the data back to where you need it, and then shut everything down for you. So the idea of a cluster is getting a bit old-fashioned with the cloud, okay? This is basically running a job, okay? And then you just specify how many nodes, where your input files are, what your executable is. And that's what the batch shipyard does, is it allows you to do that in a Docker world. So when we think about going forwards, again, how to do your research, this kind of model is really, really pretty exciting. Because once you get this set up, again, you're not thinking about it from a system admin cluster perspective, but you're thinking about it as, right, I need 10 jobs, and each job is 500 cores, and just fire them off. And so actually one researcher down at Imperial College, Simon O'Hanlon, is actually doing some next generation sequencing, some genomics research, and he had an Azure grant, and he was he was deploying a cluster. So he deployed a cluster and then put some grid engine over the top of it, and then was able to crank through all of his genomics data. And Imperial College has got a fantastic cluster. The department has a 1,000 core cluster. The university has multi-1,000 core cluster. But this is what he found, was that because he had his own cluster, he could do what he wanted. He could put whatever software on he wanted. He didn't have to queue for anything, and he could just crank out his results. So it's really kind of interesting how this idea of having, like I said, on-demand, instant, infinite computing resource, near infinite, it's infinite as far as you're concerned. We have to worry quite hard about making sure there's enough there, is a kind of new way of thinking about computing. So it's kind of this sort of masterclass is really to get you thinking in that direction, and then we'll drill down into in some other sessions in a bit more detail on that. So I want to switch gears a little bit, because that was, I said, don't worry about infrastructure, but that actually was quite a lot sort of infrastructure, VMs, containers, etc. I want to move on to some of the more platform level thinking. When we think about data science, we often think about this phrase big data. Okay? And we do have big data, but you can define it in different ways, right? Is it a big single file? Is it lots of small files? Sometimes one small file, a spreadsheet, for instance, is vitally important. So I like to think about data science as data big and small, and the combination of those things. And so I've got a few examples here, and then we'll go on and talk a little bit about some of the other aspects like AI and machine learning. This is an app. It's called eBird, developed by Cornell University. And it basically allows you, when you're out walking, if you see a bird, you can take a picture of the bird, and you can upload that sighting into their system. And so they've been developing this system for a number of years, and it's becoming increasingly popular as obviously the app gets out there more, and there are more users, so then they're aggregating more data. And so they were finding it increasingly difficult, not just to collect the data, to analyze the data in any sensible amount of time. And so I've got a little video here where the researchers there will tell you a bit about how they've been using Azure.
Ornithology really taps into our wonder about the fact that birds fly. I love the unpredictability of birds. I love not knowing what I'm going to find every morning when I wake up and go out birding.
Birds are wonderful indicators of the environment. So they tell us something about the quality of the environment that can help us to manage it better.
You go into the field, and then basically you listen to birds, you watch birds, and you record the birds that you see. And the idea was, could we somehow gather this information that somebody in India has, somebody in Brazil has, somebody in Guatemala has, and bring them together into one unified database? And we've done that with eBird.
Our goal is to try to provide information for the scientists and for decision makers in conservation. So we practice open science. We use a series of software products that are all open source. Our core for the analysis, Hadoop to be able to scale that, and we run this in a Linux environment.
We now have 325 million records, 10 million records per month.
We have gigabytes of data that go into our model. We then generate terabytes of information through the modeling process.
To analyze migratory patterns for a species across North America would take us 2.5 weeks. We need larger compute resources. We decided to use Microsoft Azure because what Azure had was a combination of cloud computing and open source tools in an environment that was easy for us to port.
Azure is not just a Microsoft solution, meaning it doesn't require you to run Windows on everything. Many people don't realize that over 20% of all of our systems out there are open source.
Azure really boils down to a large amount of compute capacity that can be accessed globally. And what it does is it says to any organization in the world, you don't need servers in your office.
The eBird team has certainly benefited because of cost reduction and time to market. It took them several weeks to get one batch done, and now they can do one batch in just a few hours.
It allows us to apply machine learning techniques. We're able to actually make almost real-time pieces of information about whether birds are increasing or decreasing, how they're changing throughout the seasons.
Thanks to tools like Microsoft Azure, we're able to show bird watchers when there are 300,000 of them working together for a common purpose, can fundamentally change how we know the world around us.
It's not just about helping birds and a way that we can use the data for bird conservation, but how we can leverage that information to help us move towards solutions to these grand global challenges.
Some Hadoop systems, and they're running them on premise and they move them out to the cloud, and like I said, with these platform services, we have one called HDInsight, which basically does managed big data clusters for you. And we rely on the open source tools and platforms. So rather than build our own proprietary kind of a Hadoop equivalent, what we do is we put Hadoop, we put Apache Storm, Apache Spark, we just put Kafka and Storm on top. So you can just deploy a cluster like I showed you before. This is what it looks like. You basically say, what cluster do I want? How many nodes do I want? Do I want Linux or Windows? Deploy. And then it deploys the whole thing for you. And so that's how easy it is to deploy clusters. We ran a training session at Manchester University about 2.5 years ago. And we did a walkthrough of this. And one of the people at the front from Computing Services was sort of head in his hands, and he was saying, what you've done, I was working on for 6 months to get this deployed on our local system. So it's really hard to do this properly and get the performance and scaling. We do it once, and we deploy it globally, and then we make it available through our web portal or through an API, so you can deploy this, for instance, from a Jupyter Notebook. So it makes it really, really sort of super easy. And what it means, and like with the eBird team, is when you're thinking about these problems and you say, it's going to take me a couple of months to chug through it, it kind of gets you into a particular way of thinking of how you can do your research. And when we think about data science, it's not about the data. It's about the information and the insight we can get from the data. And we often obsess a lot about the data collection, but the data's pretty useless unless we can aggregate it and bring it together, maybe distribute it, but then pull it into a way where it's integrated so we can run some analysis. Like the Cornell team, until they could pull all that data together and run it across a Hadoop cluster, they couldn't really get those deep insights. And what the cloud enables you to do is speed up this loop. So often we never get to this point because this takes too long. Okay, and that's where the cloud computing can really, really help. We've been working with Newcastle University on this EPSRC project on flood risk modeling, and actually working with some of the water companies. This model on the side here shows a very high resolution model of London flooding. It sees 1 in 100-year flooding events, and it's run at a 1 meter resolution scale. It doesn't just model the roads. Okay, it models the buildings and the different route types and the drainage off the buildings, and it also has a one-dimensional model of the sewerage system underground as well. So what you can see is areas where the flooding is bad because of a combination of the terrain, and they have a digital elevation model, they have the buildings, and also the drainage system where that may be getting overloaded. And so this was a kind of hero calculation they were doing on their cluster to show what they could do in London. But they're also part of a European project, and so when they got access to the cloud, what they could do is they could run this on over 500 cities across Europe and deploy it as a web app, so they could then display the results here. And so you can go, I was in Warwick the other week, so I just picked Warwick, and you can see, and they've got the results, so they ran the results in the cluster, they then put them onto the cloud, and then they put a web portal so that you can click on any city and show these events and say, this is what happens with 100 millimeters, this is what happens with 50 millimeters of rain, 200 millimeters of rain. And so it makes it really, really easy to not just compute the data at scale, but share the data. And again, they're not downloading the data, okay? They keep the data in the cloud, so all the tooling and all the web stuff is in the cloud as well. And so taking the data and turning it into information, and just even this is not really doing intelligence on it, this is just showing it in a way that's really easy to use. Otherwise, this would just be a bunch of netcdf files that nobody would be able to actually make any sense of unless you happen to be the scientist who could decode those. But obviously here at the Turing, in terms of data science, we're interested in some of the more advanced analytical techniques, things like AI and machine learning. And I've talked a lot about cloud, but at Microsoft, we do a lot of AI and machine learning. Okay, again, increasingly, companies are investing heavily in AI and machine learning. We have invested very heavily in AI and machine learning and continue to do so. You may have seen a couple of weeks ago, we actually partnered with the OpenAI group, who are going to be using Azure to do the majority of all of their research work on it, largely because of the access to the GPUs and the clusters, but also because of our large investments in that. And when we talk about the cloud now, we're actually really thinking in this direction. A lot of Microsoft itself is really going in this direction. We actually kind of reorganized the company, so we now have a division called AI and Research, and, which includes Bing and Cortana and Microsoft Research. And Harry Shum is our leader for that. So now when we talk about the cloud, it's interesting because with Azure we've got CPUs, and that's great. And you can run things like CNTK, our toolkit, Caffe, TensorFlow, Torch on CPUs, but we all know that actually to get the performance we really want to run on GPUs. But where we've taken it even further is GPUs have their own limits as well. So we have developed some FPGA technology, the programmable hardware really, where we're betting on this to get us past Moore's law. And so we've built what we call the first AI supercomputer, where we combine CPUs, GPUs, and FPGAs, and these are deployed at scale on hundreds of thousands of servers. Every new server in Azure has FPGAs now. One of the situations for that is to do faster networking, so lower latency, high bandwidth networking. Other things we can do are things like hardware encryption over the wire. The FPGAs actually sit between the network and the CPU and the GPUs. But also for machine learning. And what we did to show that is we showed how we can use an FPGA to do machine translation. And we took War and Peace, which is about 1,600 pages, and we translated the whole of War and Peace on an FPGA many times faster. It took several minutes to do on a CPU system, and we did it in a few seconds on a server. But it didn't show the scalability of the cloud. So we thought, what's a nice big corpus that's available online that we can try to translate using our new AI supercomputer and FPGAs? So we picked Wikipedia. And what we did was we took the whole of Wikipedia and we translated it from English to Spanish. And we did it in 1/10 of a second by using the FPGAs at scale. So that shows you what an AI supercomputer can do. And it was actually the first exascale computation, but exascale in terms of operations, not floating point, but still showed the capability of the real cloud AI supercomputer. And so the ability to do things like deep learning in the cloud, taking advantage of all the work we've done on HPC, but coupling those as well, is really, really powerful. And again, we announced this deep learning partnership with NVIDIA last week, with the CEO of NVIDIA, to work on this in the cloud, but also working with some of our deep learning toolkits on the new Pascal GPU systems as well. And so this is quite useful, as Chris in the front row here will test to, is that Chris here was one of our guinea pigs for using Azure for some of his work, and have you given a talk, or you'll give a talk, I guess, about your 3D reconstruction work. And so he got actually early access, because he's part of the Turing, we managed to get some early access to the GPUs, where he was able, with his research team, to run these calculations a lot faster. It so happened to, hit paper deadlines. It's often the case, you do a lot of research and you have a paper deadline, and you think, oh, if only I had more computing power so I can do better for and I can get Best Paper Award, right? And we definitely want Best Paper Awards coming out of the Turing. And so Microsoft Azure can really help with that. And Chris, you know, once he got up and running, didn't hear from him for a while. And then when I came, he said, yeah, it was good. so it really can help kind of day to day. And we can talk about that a bit more later on. And then we have our own deep learning toolkit. So if you haven't seen, there's something that was called CNTK. We've rebadged it as the cognitive toolkit. This is our deep learning toolkit. It's the equivalent of things like Theano, Cafe, TensorFlow. And it's used by our own team. So this is used by our Bing Search team and other teams like the Skype team and the Cortana team. The work that goes into this is the work that also went into Microsoft now being the leaders on ImageNet. Okay, and you may have seen that we also reached human parity for speech recognition on the switchboard speech recognition test. So we managed to reach an error rate of 5.9% on speech recognition, which is what humans achieve. And that work we package up into this toolkit so that you can use it. And it's an open source toolkit. And so it's state of the art, and it will scale across multiple GPUs and multiple nodes. It was the first toolkit that will actually run distributed across multiple nodes and multiple GPUs. And obviously that helps us do things like ImageNet and speech recognition. And so this is something that I think we'll do a deep dive on this. We're going to do some deep dive sessions in the new year, and so I think this one is an interesting one. On machine learning more generally, so that was kind of deep learning, but as we know, machine learning has lots of different aspects to it. We have a platform we call Azure Machine Learning, which makes it really, really easy to build fairly sophisticated machine learning models. And we have this graphical kind of workflow engine. And what you can basically do is you can pour data in at the top, okay, from different sources. It could be a database, it could be cloud storage, it could be just a file. And then you can basically transform the data. So you can do things, it's really, when you're doing this stuff, most of data science, as you probably know, is pretty boring because you end up cleaning up the data, refactoring the data and all that sort of stuff. So we have a bunch of different tools that allow you to do that, do dedupe and those types of things. And then we have to train the data. So we've got modules which will split the data. So you can say, okay, I want 70% of my data for training, and I want to take every other row and then put the other 30% for evaluation. And so again, we've got in here the different libraries. And then we also have our own machine learning algorithms, okay, some of the stuff that Microsoft uses. We've got a recommendation, we've got a Matchbox recommender in here, which is the Matchbox recommender that's used on Xbox Live when you fire up an Xbox One and it recommends games. It's available, that algorithm is available in here. We've got decision trees and decision forests, which are the same as the ones running in the Kinect Body Tracker and in HoloLens, available here as black boxes, okay? So that's our own secret source, but we still make that available. But you can also run OpenCV, you can run Python, you can run arbitrary R and Python code in here as well. Okay. And you can do sort of regular maths. And so this allows you to build a workflow end-to-end for data cleaning, testing different models, comparing the performance of 2 to 3 different models, evaluating them, looking at the different curves and things, and then seeing what you can do with it. But what is critical here is there's a button here, there's a web service button. And the unique thing here really is you can take the data, you can push it through Azure Machine Learning, but you can publish the model as an API. Okay, and we handle all of that for you. You literally click a button that says Publish Web Service. And it not only creates the API, it also generates a page of documentation, it generates code samples in Python and R and C#, and then that can be used by a mobile application, desktop application. One of the students here said they were running in a hackathon, and they said, if only we'd had this, we would have won the hackathon, right? Because they hadn't gone through it. It was with National Rail, and it was looking at predicting delays. And I said to her, actually, there's a tutorial on predicting flight delays, where you take in weather data, you take the historical flight delay data, you train the model, and then you publish the API, so you can put in a flight number for next week. It will go and look up the weather forecast and give you a probability of that flight being delayed, and publish as an API, so you can just build a mobile phone app. So this bit is really neat. It's a really nice way of publishing ML models, and I think it'd be nice to see how folks could do that. Team at University of Oxford has actually been using Azure Machine Learning to do just that, and so I've just got a video so they can tell you about it.
I grew up in rural parts of Kenya, which have quite high rates of poverty. In our family, we used to get on our bicycles, each of us carrying 3 jerrycans. So we'll be like 3 or 4 people, me, my uncles, and my cousins. We'll travel like 20 kilometers on a bicycle for that day to go look for water.
Over 4 out of 5 people in the world that don't have access to safe drinking water live in rural areas. This situation is particularly compounded in Africa, where hand pumps and rural water supplies often fail. And one of the newest technologies that's now emerged in terms of mobile solutions and cloud-based computing is allowing us to advance with innovative ways to address this problem. The REACH program is aiming to make 5 million poor people water secure in Africa and Asia.
Groundwater is one of the safest supplies of water in rural regions of Kenya. So being able to track the depth of the aquifer is critically important in being able to understand how healthy that water system is. We may be familiar with the idea of using one's smartphone or smart devices to carry around with us and to use to monitor our own health. And the idea here was, well, can't we put some of those mobile health devices into the handle of a pump?
So the data is really interesting. When you see a raw accelerometry pot, you kind of get these curves of the actual motion of someone pumping. When the pump is deeper, the weight of the water that you're lifting is much larger, and so there will be more vibrations, whereas when the pump is shallower, you're lifting less water, and so there will be smaller vibrations.
Imagine you have multiple intelligent nodes. They're all transmitting data. You have to integrate data in a cloud-based system from data nodes across an entire region, tens of thousands of pumps in our case. That needs to be done in a cloud-based situation where one has a huge amount of computing resource to be able to perform the heavyweight machine learning algorithms on the integrated data. We liked the inclusion of the Azure machine learning framework, which allowed us to port our existing R and Python-based machine learning tools directly into a safe cloud-based system.
Azure ML makes fitting machine learning models much faster, as I can explore the parameter space much quicker on the cloud than just on my own computer.
I think making data usable and effective decision making is absolutely critical. Policymakers and decision makers have the responsibility to take very difficult and onerous decisions, and there's a huge information deficit in terms of how they should proceed. So the ability to collect data at scale in a way that's usable and appropriate for them is extremely powerful.
Initially, it used to take more than 30 days to repair a hand pump. But now, because we have this information, when a hand pump breaks down, we can repair them within less than 3 days, or sometimes even 48 hours. So that has enabled the villages to have better access to water. My hope and aspirations is to see this system making my village and other villages back in Kenya water secure and moving them out of poverty.
Machine learning research for many years, and what the cloud enabled them to do is deploy that at scale as a web service, and that's again that combination of what you can do in the lab versus what you can do in the cloud. I want to finish up talking a little bit about reproducible research. There was actually a Turing workshop about reproducible research a few months ago. And there's very much a drive for any research that's done to be good, reproducible. And when we think about reproducible research, this is really what we mean. This is from Carol Goebel from the University of Manchester, who's one of the world's sort of thought leaders on reproducible research. The first two you should do. If you can't do the first two, you're really not a very good researcher, okay? If you can't repeat your own experiment, then you probably shouldn't be publishing it. If you can't repeat the same experiment, the same setup in the same lab, okay, at a different point in time, say 6 months down the line, again, that's not very good research practice. This is probably grounds for failing a PhD if you can't do that. At that point, you would normally publish your result. And once it's out in the open, other people might read your paper and say, that looks really interesting. I'm going to try and repeat that in my own lab. Okay? And this is probably where we are right now in terms of, is there enough data and information in the paper or in the supplementary information to the paper to be able to replicate the experiment? Okay? So this would be the same experimental setup. Then more difficult is, can I repeat the same hypothesis here, okay, and validate that hypothesis with a different experimental setup? Okay, so you could think about this, and it's very interesting in deep learning. Could I run an experiment in Theano and reproduce that result using TensorFlow and Cognitive Toolkit, right? Because that is good science, okay? So it's an interesting question. So that is what we mean about reproducible research. And it's only then that we can really even think about reusing that research somewhere else, okay? So like I said, I think we're largely here, and the majority of science is good science, right? A lot of the push around reproducibility is around the pharmaceutical world, where I think there was an experiment run where a very large pharmaceutical company could not reproduce or could not replicate 70% of the university research that they wanted to try and reproduce and then build up a drug pipeline for. So really, really quite a problem. And so there are lots of tools for this, and one of the tools that's really gaining popularity is something called Jupyter Notebooks. How many of you have used Jupyter Notebooks or heard of them? Okay, if you did your Python training, you should have done. And it's really a kind of online notebook that allows you to run documentation with executable Python code. And there's something called NB Viewer where you can publish it, and on GitHub you can publish the notebooks and you can view the notebooks. But when you want to execute the code, you need to run it somewhere. And so what we've done is our data science team has worked to build out what we call Azure Notebooks, which allows you to take a Jupyter Notebook, publish it, and then anyone else can clone it and run it in their own Azure account. Okay. And what's really nice is it's actually free. And what we've done is we actually have now taken May's Python course and uploaded it, and I've made a little short URL, Turing Python. So any of you doing the Python course that May did the first talk a couple of weeks ago, rather than installing it on your own machine, you can just click Open in Jupyter, and it will open your own cloned copy of that in your Azure account. And so it's really good for training. University of Cambridge is now using this for their 350 undergraduates in their first year for their Python course, for instance. And it's scalable. It's in the cloud. The thing they worried about when they were deploying it on their servers was they had it on one server and 350 students. They weren't sure if it was going to work. Moving to Azure, it just works because it scales. So teaching is quite nice. But for open science, it's critical. And this team, the LIGO team, who made the big gravitational waves discovery earlier in the year, have an open science center. And what they've done in the open science center is they're using Jupyter Notebooks to allow people to look at their experimental data. And so we've actually worked with them to make sure that when you look at the binary black hole events and things that they were looking at, that you can click on this button that says Azure, and it will go and spin up the Jupyter Notebooks. These are the gravitational wave experiment notebooks spun up in my Azure account. And you can go through and run the signal processing on the data. They've got the data sets there as well, all in the cloud. So the Jupyter Notebooks are really, really nice way of kind of getting into the cloud and seeing how you can make use of it. Oh, I have got one more thing, which is I think some of the things that we may be doing here in the Turing is around IoT, mobile apps and those types of things. And again, when you think about how do I build an IoT infrastructure, okay, there are people doing PhDs on how to deploy IoT infrastructures, right? It's kind of an interesting technical problem, but lots of people have the same issue. So we've worked with Rolls-Royce where we've now supporting their engine maintenance programs, so the data from their engines goes up to Azure and gets processed so they can do predictive maintenance on it. We recently deployed this system with the UK Met Office, and it's called the Weather Observations website, where if you have a weather station, you can register it with the Met Office, and you can push your weather station data into their system, so their weather forecasters and climate forecasters and scientists can have access to your data to validate their models, for instance. And so they moved this system onto Azure to get the scalability they needed going forwards, and you can click, and this again when I was in Warwick, you know, is somebody's weather station, and there's the data there. And when I say people do PhDs on this, this is the kind of infrastructure you have to build, okay? And you could build this, but we've built it as well, and we put a whole team on this. So the idea is you have events produced by devices or applications or simulations. They feed in to an event hub, it gets ingested, and then we can run processing, we can run stream processing live on it, or we can push it into storage and then do things like Hadoop on it, and then push it out into a presentation layer. So this is a single suite called IoT Suite, I can show you, we could do a session on this if there's enough interest, where you can actually single-click deploy this entire system, okay, which is a number of different technologies, and then you get a nice web dashboard and you just register your Arduino device and it starts streaming data. So again, with the cloud, this platform service of IoT as a service, you know, is really, really interesting. And then finishing up really, to pull it together really with the cloud, is we've got the ability to run websites. The Irish Marine Institute is several universities and industry working together, and they've been using Azure to deploy a number of different systems, data distribution system. They redeployed a NASA data server on a VM. They built this system with us called Fetch Climate that allows you to view climate data. And then this is running a dynamic R server. It's a Shiny R server that does dynamic visualizations of data. So it shows how with the cloud you can make your data much more kind of widely available, and they were really kind of pleased that they could pull all of it together, lots of these disparate sort of projects that they had, into one sort of solution, and they could sort of drive it forwards. I'm going to skip that video. I'm going to skip through this, which is something called Microsoft Academic Graph. I think if we want, we can have another session on this, because we did run a Turing workshop around this. This is a data set of the world's academic publications that's updated regularly. It's freely available as a download, and it also is available through a website. So this is kind of equivalent to Google Scholar. So you can look up a random name and see what publications there are, filter on CVPR, and it gives you data about the conference, for instance. So this is called Microsoft Academic. We've got a preview which allows you to do your own personal profiles, linked to LinkedIn and Facebook and things like that. But it's also published as a cognitive service. So we have these AI services called cognitive services. We have image recognition services, OCR services. This is called the knowledge service. And it's part of our network of cognitive services around, like I said, vision, speech recognition, language, text analytics, etc. Again, these are the higher level services that may be quite useful. So OCR, for instance. You upload an image and it OCRs the image and sends you the data back. Okay. Or image captioning. The British Library did this. Send up an image and it will caption the image automatically. Okay. So that's really quite a lot, actually, I've talked about. But I wanted to give you a pretty wide view of Azure, okay, because we will be doing deep dive sessions in the new year around specific topics, much more hands-on. But I really wanted to sort of take a step back, because basically, this is what you have access to, okay? And at the Turing, because of the partnership, we want to make sure that we have some, we can help you all, and also we can sort of do bigger research, bigger and better research. So, so that's what I wanted to talk about, and thank you very much. Thank you.